Hello there. Yes, welcome back to this course on discrete mathematics, and we are still dealing with this functions and functions part 3. Previously we have seen what a function is and what are the inverse functions, and today we are going to examine further on to this functions. And we know that functions can also be graphically represented, and you can either prove or disprove whether a function is onto or a function is one-to-one just by means of some horizontal and vertical test. Let's see here more on functions, graphs of functions. Let f of x is 2x plus 1, and we are here to plot x comma f of x. If that is the case, then we have to place a value for x. So let's say if x is 1, then f of x would be, yes, that would be 3. And if x is, you are going to plot that, if x is 2, then your f of x is going to be 5. Likewise, if you bind values for this x, you are going to plot the whole graph there. That's it. That line is our graph that are needed. Just we have plotted the graph of f of x. Isn't it simple? Yes. Of course, you can try with more complex functions and also see how its inverse would work out if you are taking inverse of this function, and try to graphically plot and see how this would look like. Now we are into this new topic of composition of functions. So we call f composition of g. F composition of g of x equals f of g of x. So let f of x is 2x plus 3 and g of x is 3x plus 2, and then if g of 1 equals 5, then f of 5 equals 13. Can you get this point, how it works out to be? Yes, if you just place 1 for g of x, then that becomes 5, and you're taking this 5 over to this f of x and you're placing it in the function f of x. So that is 2x 3, that becomes 10 plus 3, that is 13. Thus f composition of g of 1 equals f composition of f of g of 1, that is 13. Did you get the point how it works out? So initially you get 3 times 1 plus 2, so that is 5. That is what your g of x is. So you are putting f of g of x, so you are putting this 5 in the f of x function here. So what happens, 2 times 5 plus 3, so that becomes 13. That's how this composition works out. So here is a pictorial representation of how this can be viewed as 3 different parts. Let's say we have a, b, c, the 3 functions, or in other words, this mapping of g to a is g, this mapping of a to b is the g part, and mapping of b to c is f. Then if suppose I have an element a that is mapped to the element in the function b, that is g of a, and then if suppose I want the g of a in the function b to be mapped to an element in c, that is f of g of a. And if you want to map as a whole, that is where the composition comes in, f composition of G of A. And in fact, the whole thing from A to C can be referred as f composition of G. And in fact, you can also look back and see whether you would be able to create the inverse property of this function. Let's say here with this example, f of x equals 2x plus 3 and g of x is 3x plus 2. Just now we saw that example. Let's see how it applies to this pictorial representation of. So you have 1, and this 1 is mapped with g of x, that is 3x plus 2, which yields us the result 5. And then you are going to map that without f of x, that is f of 5 equals f of g of 1, that is 13. So you have f of g of f composition of g is g of 1 there, and that's nothing but f of g, that is f composition of g, the same thing. Therefore, f of g of x equals 2 times 3x plus 2 plus 3, that is 6x plus 7, where x is 1. And when you put 1 there, you get 13. Got it? Well, the question is, does f of g of x equals g of f of x? This is the relation that we have to prove or understand with regards to composition function. Let's try and see whether is it equal or not. Let's take the same example where f of x is 2x plus 3 and g of x is 3x plus 2, and you have f of g of x revealed to be 6x plus 7, whereas g of f of x is got to be 6x plus 11, which means that this property does not hold. F of g of x is not equal to g of f of x, as they are not equal. So the function composition is not commutative. Just keep this in mind. So let's consider a function f of x where x equals x cubed, and compute some values and graph them. So you have to give some examples for x and try to plot the graph and examine this. Always it is encouraged for you to plot the graph and examine by yourself to get a full understanding of the whole features. Let's draw it. So you have x as minus 2, 1, 0, 1, 2, and so on, and f of x is, that is nothing but the x cubed, so it's minus 8, minus 1, 0, 1, 8. For these values of x and f of x, we can try to plot the graph. Let's start with minus 8, minus 1, 0, 1, 8. That's it. And some questions you can ask yourself, is this an one-to-one function? Yes, so it will have an inverse function, because if it's a one-to-one function, if it's an, you can see that if it's a bijunction, it should be an one-to-one correspondence. If it has a one-to-one correspondence, then it will have an inverse function as well. Do you want to find what its inverse function is? So you have to undo the cube, because actually f of x is x cubed, and if you want to find the inverse, you have to undo the cube part. So in other words, you have to take the cube root, right? Yes, cube root, that's right. Let's do it. F inverse of x equals cube root of x. So again, plot it off and try to see what it takes. Let's take the value we got out from the function and put them into inverse function and try to plot them together. So let's plot the table first, where you have x as -8, 1, 0, 1, 8, and f inverses, that is cube root, which yields us -2, -1, 0, 1, and 2. So with these values you can try to plot the graph, right. So you can see how -2, 1, 0, 1, and 2 be with respect to x being plotted. And then, as usual, you can notice that x and y values trades its places for the inverse function, and then these functions reflects each other about the line y equals x, the linear line that you draws between these 2 points. You can see the actual reflection and the trading of places that happens in the inverse function. Let's see further on, if f and g are inverse function, their composition would simply give x back. So that's one of the property that we have seen once. So let's see here as well. So in other words, f composition of g equals f of g of x, that equals x, and g composition of f equals g of f of x, that equals x. So this property holds true for an inverse function. Now let's switch the topic a little bit and consider some useful functions that are found in the arithmetics as well as the mathematics. The first one is the floor function, which are represented as if having the floor there. So floor of x means taking the greatest integer less than or equal to the number, and the ceiling is like as if it's having a ceiling. So the ceiling of x means take the lowest integer greater than or equal to the number. These as functions. So round function, round of x equals floor of x plus 0.5. That's rounding the value. Well, now it's time for us to see some examples. So sample floor and ceiling questions here. So find these values. Like for example, the floor of 1.1. Well, that's 1 because we are looking at the value that is closest to 1 there. And the ceiling of 1.1 is, yes, that's true, the greatest value that we are looking at. And the floor of minus 0.1 is, right, that's -1. Ceiling of minus 0.1 is, that's right, that's 0. That's interesting question, right? Well, then the ceiling of 2.99, that yields 3, and the ceiling of minus 2.99, that yields -2. So here's some more interesting parts that you have. You have a function within a function in which you can see the floor of 1/2 plus the ceiling of 1/2 there is inside this floor. So at first what you have here is you are trying to find the ceiling of 1/2, that is 1, and then 1 plus 1/2's floor you are trying to take, that is again 1. Coming to this part here, you can see the floor of 1/2 is 0 and the ceiling of 1/2 is 1, and then you have 1/2. As a whole, you are looking at the ceiling, that is going to be 2. So ceiling and floor, they have certain properties. Let's examine that. Let n be an integer and the floor of x equals n if and only if n is less than or equal to x and x is less than n plus 1. Again, the ceiling of x equals n if and only if n minus 1 is less than x and x less than or equal to n. Again, the floor of x equals n if and only if x minus 1 less than n less than x minus n less than or equal to x. So then you have another property like the ceiling of x equals n if and only if x is less than or equal to n, and again n is less than x plus 1. So here x minus 1 is less than the floor of x, that is less than or equal to x, and that is less than or equal to the ceiling of x, that is less than x plus 1. You got that idea? Try to put some examples and check it out. Try to put some values as well and see whether you get that point, because these are some of the properties of ceilings and floors. Minus x is the floor of minus x equals minus of the ceiling x. That's interesting property, right? And then again the ceiling of minus x equals minus of the floor x. X plus n ceiling, or it's actually the floor of x plus n equals the floor of x plus n. Let's see these properties again, like the ceiling of x plus n equals ceiling of x plus n. Let's try to do some parts with the rules. Let's see the 4a, the rule 4a, which is the floor of x plus n equals floor of x plus n. We are taking that rule here, where n is an integer, and we will use this rule 1a as well, which is the floor of x equals n if and only if n is less than or equal to x and x is less than n plus 1. Let's try this direct proof, in which we can say m equals the floor of x, thus m is less than or equal to x and x is less than m plus 1 by the rule 1a. Let's add n to both sides. So we have m plus n less than or equal to x plus n less than m plus n plus 1. Right? We are here, right here now. Then by rule 4a we have m plus n equals the floor of x plus n. Since m equals the floor of x, m plus n also equals the floor of x plus n. So that's where we are getting close here. Thus floor of x plus n equals m plus n, and that equals the floor of x plus n. So we are just simply applying the rules and try to manipulate using this direct proof method, and we conclude it. Factorial is denoted by n factorial. In fact, factorial can also be defined by means of a function. So n factorial equals n times n minus 1 times n minus 2 times so on, 2 times 1, yeah, it goes on. So the 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, that is 720. So note that 0 factorial is defined to equal to 1. That's interesting part as well. We are here to prove or proving function problems. Let f be a function from a to b, and s, let's say S and T be subsets of A. So we are asked to show f of S union T equals f of S union f of T. The next one is f of S intersection of T equals, or it is a subset of f of S intersection f of T. Well, here as we have seen these function questions given to us, just relate what we have seen earlier in the properties of functions, and remember here we are trying to show with respect to sets and subsets. Yes, they are coming together now. F of S union T equals f of S union f of T. So we will show that each side is a subset of the other. So there are two cases. First we have to show that f of S union T is a subset of f of S union f of T. The other part is f of S union f of T is a subset of f of S union T. Let us talk about this. Let B is an element of f of S union T, thus B equals f of A. For some A is an element of S union T. So you got B as an element of the union, and B is a part of f of A, and you know that A is an element of S union T. Either A is an element of S, in which case B is an element of f of S, or A is an element of T, in which case B is an element of f of T. So thus B is an element of f of S union f of T, because once you know either B is an element of S or B is an element of T, anyway when you are taking the union it becomes definitely part of the union. In either one case it has to be true. Then let us show f of S union T is a subset of f of S union T. So here the second part that we have to prove here is f of S union f of T is a subset of f of S union T. So let B is an element of f of S union f of T, then either B an element of f of S or B is an element of f of T, or both, right? That is the basic property of the union, or it is like a OR function. It has to be part of S, or it has to be part of T, or it can be part of both S and T. Thus B equals f of A for some A is an element of S or some A is an element of T. In either case B equals f of A for some A equals S union T. That is the simple proof. And we have to prove the function problems like f of S intersection T is a subset of S of f of S intersection f of T. The same methods we are going to use. Let B is an element of f of S intersection T, then B equals f of A for some A is an element of S intersection T. So this implies that A is an element of S and A is an element of T, because it is an intersection part, so it has to be part of both the elements. Thus B is an element of f of S and B is an element of f of T. So B is an element of f of S intersection B is an element of f of S intersection f of T. Again, proving function problems, if let us say f be an invertible function from y to z and g is an invertible function from x to y, show that the inverse of f composition g is inverse of f composition g equals g inverse composition f inverse. It's an interesting proof that we are asked to show. So let's say we have z is an element of z and x is an element of x, and f composition of g, composition of g inverse, composition of f inverse of z equals z, and g inverse composition of f inverse, the whole composition with f composition of g of x equals x. So with this properties, you can see how the step-by-step activities are going on here. So initially you come up with this composition where you are bringing in f inverse of z, and then you are taking again the composition where you are taking g inverse of f inverse of g, and then you know that the whole stuff g and g inverse been taken, so you have f times f inverse of g, and again f and f inverse are gone, finally you have z. That's looks simple, but in real times if you really want to have the composition of these functions, yeah, we have to manipulate and we have to try to see whether it fits into our proof. So today we talked about various properties of functions, especially some of the properties that involves other functions like ceiling, like floor, and factorial functions. So talking about functions, function itself is a huge topic in which we can examine, we can do a lot of stuff in general. So whenever you input an element and it goes through a process, so this process has been defined by the function and an output is taken out of the function. In programming terms, you can also view the same idea. You write a function in which once you feed the function with some inputs and it does a process and you are expecting a certain output from the function. Likewise, the function that what we studied today is very similar cases, but we are purely working on the math point of view. Now, right now you know the differences and similarities that a function has with that of set, and later on when we talk about relations, we will also see the differences that functions and set has, as well as the differences that relations and set has. So that's it for this series of lectures that we have in functions. With this we conclude this topic on functions, and I am looking forward to see you again in my next lecture. Until then, have a good time and see you there. Bye.